All right, so in the picture below, a car is driven at constant speed over a circular hill, and we want to find the normal force in the driver when they pass at the bottom of the valley. And in this problem, we kind of encounter the number one thing that I find that throws students off in circular motion problems. There's just something about the fact that it's moving in a circle that completely confuses students. And so I want to dig into Newton's laws a little bit more profoundly well, twofold. Number one, I want to reinforce Newton's laws because they're the basis of what we do in physics. And more importantly, Newton's laws are actually a real practical way to understand what's going on with force problems so that you can actually solve them. They're not just these rules or add-ons that, well, we got to go through Newton's laws and I'll just sort of hope I can sort of hang on until we really learn how to do problems. And that kind of dichotomy is not how physics works. Let me explain. So Newton's first law basically says, and I would actually urge you to look at the haiku page where I have a quick summary, but Newton's first law basically says when you add that, Newton's first law, we'll say it like this, if an object isn't accelerating, the force is balance. Okay, I wrote that shorthand. Okay, so if an object isn't accelerating, force is balance. So let's look at this object and we ask ourselves, is it accelerating or is it not? And how do we know? So the question we're going to ask is it accelerating? And what's the criteria for accelerating? Well, it's got to be doing one of three things. It needs to be speeding up, or slowing down, or it needs to change direction. So in this problem, we're told that we keep a constant speed, so that actually rules out speeding up and slowing down. But look, it is actually going on a curve. When I say changing direction, I literally mean any deviation from absolutely perfect straight line motion. So this car, this is absolutely perfect straight line motion. And clearly this car does not follow that. Like if the car were doing this at a steady speed, we'd be absolutely fine in saying that there is no net force. But the fact is, it is not moving in a straight line. It is changing direction. And therefore, we must conclude that it is accelerating. Okay, so why do we care? I'll tell you why we care. Because when I ask students to draw the free body diagram of this car, here's what they'll do. They'll say, all right, I've got a normal on the car due to the ground. Sorry, a normal on the car due to the road. And I've got the weight of the car due to the earth. And they'll say, oh yeah, these balance because they've always balanced. And you just completely forgot everything that we just argued over here. We are forced to conclude that the object is in fact accelerating because it changes direction, which means the answer to this is yes. So that means, so this no longer works. This says the force is balance, which you wrote here. But you told me it's accelerating because it changes direction, which means this equation does not work at all. So now we look at Newton's second law. Okay, and by the way, you shouldn't do this on the AP. I'm running through the argument based on lecture as to how we set this up. So Newton's second law tells us that when forces do not balance, the object accelerates. So we'll say this as when forces don't balance, the object accelerates. Okay. So now let me go ahead and actually set up part A and part B. And by the way, I'm going to give you one more sign convention for this. We're going to define in this problem, we will define, okay, in this problem, we will define down as negative. And so let's go ahead and set up Newton's second law for a car at the top of the hill. So at the top of the hill, here's the car. And here's the idea. I have the weight of the car due to the earth. And this is the left side of the illustration. And I have the normal force on the car due to the road. Now, when I use Newton's second law, what I'm forced to conclude is I have the normal force pointing up and the weight pointing down. And with circular motion, the acceleration points towards the center of the circle. So we are forced to conclude that since it is changing direction, there is an acceleration that we call circular acceleration. And again, to be clear, we're told that at the top of the hill, the normal force on the driver car seat thing is 0. So that tells us this value is 0. And so we're going to end up getting negative mg equals m. And now, right here, we finally account for the fact that it's circular motion. And we put in v squared over r for the acceleration. So that's going to be v squared over r. And then we're going to end up canceling. And by the way, since this is at the top of the hill, and with circular motion, the acceleration is defined as being towards the center of the circle, this is going to be negative v squared over r, because that's the direction of the acceleration. So this cancels, and what we actually conclude is that g is v squared over r, and we're stuck and we can't do more with this. So we need the right side to go further. All right, so now we look at the right side. It's going to be, so here we go at the bottom. We've got the weight here. We've got the normal force here. Now the acceleration is towards the center of the circle, which is upwards. So we have the normal on the car due to the road. We have the weight of the car due to the earth. And we have the following equation again, the normal and the weight. Normally these would balance, but they're actually having a tug of war, and the effect is that the car accelerates in a circle. Now at the bottom of the hill, we're told the normal force is not 0. So let's just see where this goes. So we have the normal on the car minus mg equals m. But now we have a positive acceleration upwards because the direction of the acceleration when you're moving in a circle is towards the center. Now what can we conclude? Well, from the left side here, this equation, which I'll call equation 1, can now be substituted into here. And so what I end up getting is the normal on the car due to the road minus mg equals m times g. And so what I conclude is that my normal force on the car is in fact equal to 2 mg. And when I actually calculate that out, that's going to be 70 times 10 times 2, 1,400 newtons worth of force. So that's problem number 1.